So in the last class, we discussed about the rotation of molecule. So we will continue from that. So when you consider any molecule, they possess rotational motion, but the molecule they are having the permanent dipole moment. Only those molecules have this rotation spectroscopy, or only they will rotate when you apply some microwave radiations to those molecules. And then it's discussed about the moment of inertia is associated with two-body problem, and we found that I will be equal to mu times r square. So this mu is nothing but m1 m2 by m1 plus m2. That is the reduced mass of those two masses m1 and m2. Now, depending on this I, moment of inertia, we can classify the molecule into different groups. That we will discuss in this section. So, if we consider any molecule, let's consider a molecule as you can see from here, this red color. Assume that this is one. This sphere is representing a molecule, and the center of mass of this molecule is at this point. And if you draw three axes uh, along this center of mass, as you can see from this figure, these axes are A, B, and C axes. So then we have different moment of inertia, IA, which is the moment of inertia about this axis A, and then we have IB, which is the moment of inertia about this axis B, and IC is the moment of inertia about this axis. So if you consider any molecule like this, the moment of inertia, because of that rotation, their rotation will be different in this axis, along this A axis, along this B, and along C. If you consider this moment of inertia as IA, IB, and IC, then this moment of inertia will be different for different molecules. So in conventional way, what we'll do, we'll denote IC as the moment of inertia, which is having maximum value, and then IB, and then IA, which means that in a particular molecule, if you consider different moment of inertia in different these three different axes, which axis is having the greatest moment of inertia or largest moment of inertia, that is denoted by IC. And the lowest moment of inertia axis will be denoted by that A, axis A, and corresponding moment of inertia will be IA. So conventional method of representing this moment of inertia corresponding to these different molecules is that IA will be the smallest moment of inertia, and IC will be the largest moment of inertia, and IB is the in between. Okay, so if any molecule which is having these three different moment of inertias, then corresponding in that molecule, which one is having or which axis is having maximum moment of inertia, that is labeled as IC. Which one is having minimum moment of inertia, corresponding we are talking about axis, and the corresponding moment of inertia will be IA. So IA will be the minimum and IC is the maximum. That is the conventional way of representation. And as we discussed, the moment of inertia corresponds to different masses will be given by sigma I. So this will be sigma I times mi ri. This is the equation for moment of inertia. So it r1 square plus m2 r2 square plus etc. So this r is the perpendicular distance towards that particular axis. So in this particular case, we have three axes. So each molecule, in each molecule, there will be different atoms, and each atoms are having different masses, and those masses will be separated from its mass, center of mass of that molecule, and how much is that distance of those atoms from these axes? That is denoted by this r. So that is the perpendicular distance from the axis of A, B, and C. I will explain that in the next. So this is just representation of those moment of inertia. So if you consider any molecule, consider the center of mass, draw these three perpendicular axes A, B, C. Correspondingly, we have different moment of inertia IA, IB, and IC. So this moment of inertia IA, IB, and IC will be different for different molecules depending on number of atoms in that particular molecule and the rotation. Okay, and so in conventional way, we will represent IC as the maximum moment of inertia, and IA as the minimum moment of inertia, and IB in between that IC and IA. And for different molecular symmetry, we have different moment of inertia along these axes. Now, depending on these values of IA, IB, and IC, we will be having different classes of molecules. Molecules are classified on the basis of that. So, for example, if you consider, okay, let's consider the calculation part first. So, if you consider the water molecule is having this V shape. As you can see from here, it will be having some bend shape. It's not linear. So they are having some angular separation. This is about 106, 106 point something, 104 point. So that is the angular separation between these two OH bonds. And now if you consider this particular water molecule, how we will calculate the moment of inertia in this case? Let's consider the previous equation. Then we can have, for example, if you consider IA, I'm just representing those. I will just show one case. So if you calculate one IA, so what is IA? IA will be sigma I mi ri square. So that will be given by, in this case, there are different masses. Masses means different number of atoms in this particular hydrogen, sorry, in this water molecule. So we have two hydrogen and one oxygen. Now we have three different axis is ABC, and the center of mass is from this point. This is center of mass of this water molecule. So this is the point where the mass, all the mass of the water molecule is concentrated, and that is the origin. That is the origin of these three perpendicular axes. So in that case, now if you consider these masses of hydrogen and masses of oxygen, then we have in the first case, let's say MH, the hydrogen of mass of hydrogen. So MH, here we have the if you consider IA, which means that we have to take this R is the perpendicular distance from the axis. Okay, so we are considering now the A axis A. So we have to consider this particular axis A, and if you take that, the separation from that axis to this hydrogen, the distance from that axis, perpendicular distance from that axis to this hydrogen is denoted as RH, and the perpendicular distance of this hydrogen from the same axis A, which is also RH because they are symmetrically displaced, so they are having same separation from this center of mass. So from this axis, so from the axis A, they are having same distance, perpendicular distance. So these two hydrogen are separated from the axis A with the separation or the distance of RH. Okay, so I will multiply this MH with RH square, that is the perpendicular distance of the first hydrogen. Plus I can take the second hydrogen, MH into RH square again, because RH is constant, MH is also same. Then we will be having the third atom, which is the oxygen. So plus mass of oxygen times, what is this value? This perpendicular distance of this particular atom, that is oxygen, from the axis A, that is 0 because oxygen is in the axis A. Okay? Since oxygen is in axis A, the perpendicular distance from axis A will become 0. So this is multiplied with 0. So the total moment of inertia will be 2 times mh rh square. So this is just an example how we calculate this moment of inertia in this particular any particular molecule you can calculate like this. Similarly, you can calculate what is IB if you know what is the suppression of this hydrogen atom from this axis B and this hydrogen atom from the same axis. So both of them will be having same suppression with respect to this B also. And then we have to consider the oxygen also because from this B axis, if you consider the oxygen is having this much of suppression. Okay. So in that case, oxygen mass of oxygen into this suppression also will come. That suppression has to be taken care of. So three terms will come for IB calculation. Similarly, you can calculate IC also. So this is how we will calculate IA, IB, and IC. So I will just represent for IB. Just represent this IB sigma I mi ri square. So let's say this is the perpendicular distance. This perpendicular distance I will just take it as RBO. That is from B to the atom O. Then I will take the suppression of H from, that is perpendicular distance from axis B for this particular hydrogen atom. I will take it as let's say RBH and this two will be same. So that will give me some like if they are having this kind of a symmetrical structure, which means that they are in the plane, this plane of what you can see, that is the board or screen. They are just in this plane. Say that these hydrogen atoms are this plane. That is your screen. In that case, then I can write mh times r rbh. rbh means the separation of that hydrogen atom perpendicular distance of that hydrogen atom from axis B. So this square plus again hydrogen atom rbh square plus I will be having that oxygen atom contribution also, because they are displaced from the axis B now. They are not in that axis. This oxygen is not in that axis, so they are also displaced with the distance of RPO. So I have to write RPO. So as you can see, this IA, which is not equal to IB in this case, obviously. Okay. And similarly, you can calculate what is the value of IC also. Take the same kind of analysis, and the suppression from IC also will be different for this hydrogen and oxygen. Then you can also find that IB also not equal to IC for the water molecule. So what I'm saying is that depending on these values of IA, IB, and IC, then we can calculate, then we can classify these molecules accordingly. Okay? So what is the significance of this moment of inertia? This moment of inertia will give you the spectral line displacement differently. So if you say, if you remember that B value is nothing but h by 8 pi square IC. Okay, in the last class we discussed this. So B is equal to h by 8 pi square IC, and we have that spectral component which is coming from that any molecule which are displaced like 2B, 4B, 6B, etc. So as you can see from here, suppose you are having the lines 2B and 4B, and some separation between these two will be 2B. Okay. So that B is coming from here, and that B is inversely proportional to your moment of inertia I. So if you are having different moment of inertia, then you will get different spectral width at the output when you are providing some microwave spectroscopy. Then if the molecule is rotating, it will emit some microwaves, and that microwaves will be displayed in this kind of fashion, to be like that. Different lines will be coming, so each one will be separated with a distance of 2b, and that b you will get from that spectral analysis. You can get what is 2b value, and that 2b, if you substitute here what is the b value, then you can find out what is the moment of inertia corresponding to that molecule. Then that, from that moment of inertia, you can calculate what is the atomic distance in that molecule. Okay. So this B value is directly depending on your I. So different I will be having different B value, and that I is coming from here. And why it is having different value? Because if you are having moment of inertia which is larger, your B will be small. Or if you consider that energy equation also, will be having h square by 8 pi square I into that quantum numbers, J into 1. So if you consider this energy also, it's in joules. So if you consider this energy also, you can see that the energy is inversely proportional to your moment of inertia. So if you are considering the rotation of molecule, the energy of that particular rotation will be higher for the molecule which are having moment of inertia about that particular rotation which is smaller. So they are inversely proportional. If the moment of inertia is larger, then the rotational energy will be smaller. If the moment of inertia is smaller, then the rotational energy will be high. Okay, so this moment of inertia is having great importance in this particular analysis of this calculation. Now we'll discuss how these molecules are classified on the basis of this uh, moment of inertia. So first one is the linear molecule. The first classification, that is the linear molecules. So linear molecule, as you can say, their atoms are displayed in on a straight line. Atoms are atoms are deployed as straight line. So example HCl, you can see. If you consider the HCl, okay, if you consider HCl molecule, so their atoms are deployed in a line. So if you consider this particular line, their atoms will be in that particular line. So that kind of molecules, you can say they are linear molecules by means of their representation. Okay. Then how we can classify them in terms of moment of inertia? If you consider the different axes, three different axes, where the center of mass of this particular molecule will come. So the center of mass will be at near to that chlorine, because chlorine is having more mass as compared to hydrogen. So center of mass will be near to this chlorine atom. Let's say this is the center of mass position. So with this center of mass position, we have three different axes. This we have three different axes. One along this. So that center one is the center of mass position of this particular HCl molecule. And then we have three different axes like this. So now what is, which one will be the axis A, which one will be the axis B and C? That is, that we have to denote with the help of the moment of inertia calculation. So the moment of inertia, where the moment of inertia is minimum, that will be your axis A. So if you consider the rotation of molecule, this particular molecule, if you consider, then you can easily see that the molecule will be having larger moment of inertia in this axis, about this axis and this axis, because the molecule can rotate like this about this axis. So I'm just I write it like this. So, yeah. So the molecule can rotate it like this about that perpendicular axis. That is nothing but the can rotate like this. So this rotation is about that perpendicular axis. So here what is happening? This here we have that chlorine and here we have hydrogen, and there is their bond, and they are rotating like this fashion. Okay, about this this axis. Another rotation possible is that this CL. So this is about this perpendicular axis. Okay. And another rotation is possible is this one. The rotation. So this kind of rotation is also possible. So in this case, which axis you have to consider? You have to consider this particular. So with respect to this axis, it can rotate like this. So this is for chlorine, this is for hydrogen. So it can rotate like this. So with respect to that axis which is coming out of this screen. And another rotation which is possible is that we have H here, then we have chlorine here, then they are separated with this tens. And the chlorine can rotate like this. The hydrogen can rotate like this, the same fashion. So I think the person that doing that. Let's consider that chlorine is rotating your chlorine atom. So chlorine also will be rotating. Both will be in the same direction. So it can rotate like this. So about this axis, it can rotate. So this is your third axis. But as you can easily see from here, in this axis, we have the moment of inertia which is minimum because the masses are in the same axis. They are not separated from the this particular axis. Okay. So this axis will be having minimum moment of inertia, this particular axis, where the molecule is there. Uh, uh, and then these two axes, if you consider, this hydrogen and chlorine, so their center of mass will be somewhere here. Okay. So don't confuse with this diagram because I have given the axis at the center, but actually this will come from here. Okay. So, but if you consider those two rotations, then you can easily understand that both of them are having same value. So actually that will come. Consider that rotation. So axis will come from here, here because center of mass is close to this chlorine. And similarly for that the other case also, we have that center of mass which is coming here, chlorine. This is sorry, this axis is this one, right? With respect to this axis, it is. So I'm just representing that in each second it will be different. Okay, I'm just representing that how it is rotating. But in the next time, this chlorine will come here, and in the next time, chlorine will be here. Okay, when the chlorine is here, your this rotation will be like this. Okay, with respect to that axis, the rotation will become like this. So I'm just representing it just in order to understand how it is going to happen. Similarly, in this case also. Okay, so chlorine will be coming and that suppression, so somewhere here it will be like this. So after some time it will become, this chlorine will be here and hydrogen will be here, so it will be rotating. So the position I am not saying it will be having this kind of track, but overall it is having some kind of that kind of path it will follow. Okay, so that's about the rotation. And if you consider to this axis, with respect to this axis, we have two different masses, hydrogen and chlorine, which is rotating about that axis. So the mass is larger because two atoms are there, chlorine and hydrogen. They are well separated from this axis. So there will be enough distance, perpendicular distance from this axis. So the moment of inertia will be higher in this case. Same scenario you can see from here. Whatever distance you are having this chlorine from this axis, that will be same as what of this axis. So if you consider the separation of this chlorine and this hydrogen from this axis, okay, so that is this distance. Okay, that will be equal when you consider the same with respect to this axis, the separation of this chlorine and hydrogen with respect to this axis, that will be same with respect to this axis. If you consider that distance, you can take it like this with respect to this axis, with respect to this axis. So that separation will be same, and the masses are also same. So these two, this axis and this axis, the moment of inertia with respect to about this axis and about this axis will be same because they are having these masses which are deployed with the same perpendicular, same separation from those axes, and they are having same masses also. So they will be having same moment of inertia. But when you consider this axis if you consider that that will not be having that moment of inertia because why it is not having, because this chlorine atom, this hydrogen atom lies in this axis, so the perpendicular distance will become zero. As we discussed in the previous case for water molecule, we have taken moment of inertia for that oxygen atom, which is equal to zero because oxygen lies in that IA axis, okay? Axis A. Similarly, in this case, these both of these atoms, hydrogen and chlorine, lies in this particular axis. So they are not separated. They are not having any perpendicular distance from this axis. So this will be having zero moment of inertia, or this will be having minimum. So I will say this is the axis A because this is having minimum moment of inertia, and this we can take as IC or IB. So this is IC and this is IB. Okay, and this will be your IA. So this is your A axis, this is your C axis, this is your B axis. Why this is A axis? Because in with respect to or about this axis, the moment of inertia is zero or the minimum. So where the moment of inertia is minimum, we have treat that axis as A, and corresponding moment of inertia will be IA. Okay, that is the conventional method. And as we discussed about this IC or about this C axis, this perpendicular separation or perpendicular distance for this chlorine and hydrogen about this C axis is same as the perpendicular distance of chlorine and hydrogen about this B axis. Similarly, both are having same hydrogen and chlorine atom, uh, which is rotating about those axes, C and B. So they will be having same moment of inertia because the perpendicular distance and atoms both are same. So IA will be equal to, or I will put first IB and IC. So IB equal to IC, and which is not equal to IA. Is not equal to IA, and IA which is equal to 0. So this is the condition of moment of inertia for the case of linear molecule. For linear molecule, IA equal to 0 and IB equal to IC. Now there are another set of molecule. Here they are symmetric top molecules, second class, which are symmetric top. Symmetric top. So in this case, symmetric top molecule, we have two different kind of them. So one is called as prolate, prolate, and the second one is called as oblate. One is prolate, and the second one is oblate. So what is the difference between these two? What are the difference? So let's consider the case of CH3F. Have an example. For prolate, we have taken an example as CH3, CH3F. So in this case, you can see your fluorine atom is here. Okay. Then you have hydrogen atom which is into that plane. You can take. Then you have hydrogen atom here. Another one is here. So now, if you consider the IA, consider IA. So you can say now why I have taken this axis as A. This is my axis A, and about this we have that rotation of molecule like this. Okay, then I have taken this as my axis B, and the rotation of molecule will happen about this axis. And this is my axis C, this is axis C, and the rotation of molecule will happen like this. My axis. Now, why I have taken IA or A axis as this one? Because when you consider this CH3F molecule, you can easily see that this F is in the axis A, so that it will be having only 3 hydrogen which is rotating. So this 3 hydrogen will be rotating like this about that axis A. Okay, so this is your axis A. So the hydrogen, 3 hydrogen which are uh, deployed like this. So one is into that screen, they will be like this. And these 3 hydrogen will be rotating like this about this axis A. But when you consider the axis B and C, we have rotation of the entire molecule. So we have in that case, for example, if you consider B, axis B, then we have 3 hydrogen, right? And 1 fluorine also, because fluorine is not in that axis B. So we have to consider the center of mass of this particular molecule is coming near to that fluorine atom, because fluorine is having more mass. Others are hydrogen, so they are not having that much mass. I mean, comparatively smaller. So your axis B is this one. This is your B axis. So with respect to this, the molecule will be rotating like this. So you can picturize that molecule is rotating like this. So we have 3 hydrogen and 1 fluorine which is rotating about axis B. So the mass is larger in this case. Okay, so in the first case, if you expand that sigma mi Ra square as your moment of inertia Ia, then you can have maximum 3 masses of hydrogen and their separation from that axis. So we'll be having 3 mRh square. if they are symmetrically placed, because both of three of them, all of them are hydrogen, they are symmetrically displayed from that axis A, so I can take it as 3mH square. But when you consider that IB, when you consider that IB, what will happen? We have these three hydrogen atoms, which are separated with some distance from the axis B. That hydrogen, so I will just put this IBH, that is the contribution from hydrogen atom, plus I will be having IBF also, because that moment of inertia contribution is coming from this fluorine atom, which is also separated from this B axis to this much of distance. So we have all those atoms in this particular case. Since we have more masses, we will be having more moment of inertia in this particular case. The moment of inertia corresponding to the axis B will be larger. Similarly, same rotation will be there for C also. If you consider the rotations, just show that. If you consider these rotation of that molecule in different axes, then you can see for B we have this kind of rotation. About that B axis, you imagine in 3 dimensions, it will be like this. And about this C axis, okay, I will. About this B axis, it will be like this. So this hydrogen and fluorine will be rotating like this about that B axis. And about this C axis, the rotation will be like this. So the entire molecule will be rotating. So the rotation is like this. With respect to this axis C. Okay. So in that case also we have fluorine, hydrogen, and this hydrogen. So in the first case your fluorine will be here. You will be having hydrogen atoms. Hydrogen. In the second case, your fluorine will be somewhere here. Okay, and you will be having your hydrogen atom here. So the fluorine atom is now rotated about this axis C like this. And the next time, the fluorine will be here, and your hydrogen atom will be somewhere here. Just drawing it roughly to show how it is going to happen. So initially, your fluorine atom was here, and then it will be here. So with respect to this C axis, I am saying rotation with respect to that C axis. So the entire molecule will be rotating like this. With respect to that C axis, it will be rotating like this. Okay. So in that case also we have same moment of inertia as that of for B with respect to that the case of B. Both of them will be having same moment of inertia because entire molecule is rotating. So in the case of C, it will be rotating like this it will be rotating. In the case of B, it will be rotating in this fashion. So the entire molecule rotate. We have three different three hydrogen atom and one fluorine atom which is rotating about that axis. So our IB will be equal to IC. So with respect to B and with respect to C axes, the moment of inertia will be same because entire molecule is rotating and separation of fluorine and hydrogen atom about those axes are same. But when you consider A axis, okay, the fluorine atom is in this A axis, so fluorine's contribution will not be there because the separation perpendicular distance from the A axis for this fluorine will be equal to 0. So that moment of inertia will become 0. But all other hydrogen atoms contribution will be there, but that will be less than that of IB and IC, because in IB and IC both this fluorine also will come. So in that case, IB equal to IC, okay, and that is greater than IA. That's why I put A as this axis, because with respect to this axis, I am having minimum moment of inertia. That will be my A axis A. So this kind of molecule which are having IB equal to IC, IB equal to IC, and which is greater than IA, this kind of molecules are known as prolate molecules. And there is another kind of the same symmetric top molecules, and we take the example of BF3. And in this case, if you want more example here, CH3, we have CH3Cl also as another example for prolate molecule. Okay. Otherwise, you can take CH3, iodine, all those compounds, chlorine, chlorine, bromine, iodine, all those things. And if you consider the case of BF3, we have the central atom, which is B, which is your B atom, and that will be the center of mass will also be the same position of this B. And we have different fluorine atoms which are symmetrically displayed from this P, but center of mass will be at this point because they are symmetrically displaced from this particular P value. That's boron. And then we have to consider different moment of inertia, and you can see if you take those axes, then now in this time I am taking this as my axis C instead of A, and this will be my axis A. Why? Because this fluorine atom, which is in this axis, and the moment of inertia because of this fluorine atom will be 0 about this axis, because there is no perpendicular distance because the fluorine atom is in this axis. So the moment of inertia for this particular fluorine atom about this axis will be 0. So only these two fluorine atoms rotation will be affecting on this axis. So the moment of inertia about this axis is minimum. So that I will call that axis as A. Okay, both this B and F, which are coming out of the plane, so they will be in the same axis. This fluorine also will be in the same axis, that is in the B axis, but they are coming out of this plane. Both are coming out of the plane. Okay, so this one is going up, this in this right direction. So this is your plane, that is green, and then this one is coming out of the screen. So this fluorine also coming out of the screen. So they are in the same axis. And so IA will be equal to IB in this case, because for IB we have rotation of these two fluorine atoms will be rotating with respect to this B axis, and for A axis we will be having these two fluorine atoms that are rotating about that A axis like this. So, but this fluorine is coming in the other side, out, that is into this screen. So in the representation it is coming above, but it is in that. So its rotation will be like this about that B axis, sorry, A axis. So that will be like this, rotating like this. So A axis here, so they will be rotating like this. So both of them will be having same moment of inertia. So I think I have understood here this fluorine atom. This fluorine atom also will come in this B, so that IA will become IB. Because both of them are having two fluorine atoms which are rotating and their separation perpendicular distance about that axis also say. So IA will become IB and IC is larger because in for the case of IC we have three fluorine atoms which are rotating and there is no fluorine atom in this axis. So conventionally IC should be larger as we discussed. IC should be uh, greater than or equal to IB greater than or equal to. This is the conventional method of representation of this moment of inertia. And this particular molecule is called as oblate molecule when IA equal to IB, which is less than IC. So two moment of inertias are same, which is less than the third one, that is oblate. And in the prolate case, two moment of inertias are same, but which is greater than the third moment, that is prolate. And if you draw that, it will come as if you want to draw that this case, so it will come as so in this case. So if you consider this is your IP and this one is IC, so these two will be having same moment of inertia. So let's consider this is the IA value, this is IB value. So they will be forming like this kind of structure. So they will be like this. But your IC is sorry, IA is larger. IA is this. In this case, IA is this. So I will have to draw it somewhere here. This is your IA, which is larger than the other two. So it will come like this. And it will also have IA and IA. So basically, it will form structure like this. It is a three-dimensional structure. So that molecule of inertia. So it will be like this. And this structure, this is called as prolate molecule. And if you consider this case of plate, what will happen? You will be having IA equal to IB. So your IA is this, IB is this, and your I think I have made again this. IA should be smaller here, right? So or you can just say that you can take it in any way. So depending on your axis, you can change the axis so that you can keep this structure. So IA should be smaller and IB and IC. Yeah, if you draw that. So just consider that IA, IB and IC axes and draw that particular. I think okay, that's it. So the structure it will come in a different fashion. So it will IA will be equal to IC and which is greater than IA, that is for prolate case, and in the case of oblate we have IA which is equal to IB and this the IC is large. Okay, so it depends on where you draw your IC, IA and IB. Okay, depending on that it will be having different shape. But if you fix that values, then you can get that kind of a structure. So like this kind of structure, or in this case you get this kind of structure. you have to take IC. This, if you take this as your IC, in that case it will be, this will be larger, and this two will be same. IA and IB will be same. Then we'll get this oblate structure like this. And if you take the same kind of concept here, you take IC here, so that your IC is smaller, and your IB and IA will be, had to be same. They are larger than IC. So just draw that. Okay. So this is your IC, and this is your IA and IB. They are having same values. So this is the prolate structure, and this is the oblate. It depends on where you take your IC and IB values. So depending on that, structure may vary. Okay, so that's about oblate and prolate molecule for symmetric top molecule. And then we have the third one, which is known as spherical top molecule. Spherical top molecule. In the case of spherical top molecule, we have both IA equal to IB equal to IC. All are same. An example for this is CH4. So in the case of CH4, we have central carbon and 4 hydrogen which are symmetrically placed from the carbon. They are having same bond length. Now, if you consider any moment of inertia, IA in the axis of A, B, C, then we'll be having same moment of inertia in all the axes. IA, so IA will be IB equal to IC. So all of them will be same value. So in this case, you can consider the plane like this. So they are kind of structure. So these two hydrogen come above and below this plane. Okay. And these two hydrogen will be in D. Now, if you take any of those moment of inertias, then we'll be having, because all of these are symmetrically displayed, and the moment of inertia IA equal to IB equal to IC. And in this particular case, we do not have any dipole moment change. So there is no dipole moment in this particular case because they are balanced each other. So in this case, the microwave is inactive, or this particular spherical top molecule, they will not show microwave spectrum, or they are inactive to this microwave spectrum. Okay, so there will not be having any rotation. Means that if you, even if you rotate those molecules, they will be having same kind of structure, same kind of symmetry. And the fourth one is that asymmetric top molecule. So asymmetric top molecule, in the asymmetric top molecule, we have IA not equal to IB not equal to IC. And one example we already discussed this, water molecule, top molecule. And we have already shown that IA not equal to IB not equal to IC for the case of water molecule. Okay. And another example is think this is formaldehyde. Okay, so these are the classification of molecule on the basis of the moment of inertia. They are classified as linear, then symmetric top, then spherical top, then we have that asymmetric top. And in this case, if you consider the spherical top IA equal to IB equal to IC, if you draw that, then you will get a sphere. You consider this as your center and IB equal to IA equal to IC, then you will get a sphere like this. That is the spherical top. And in this case, nothing will be equal. So this you can represent by a there are different log for this. I will just show that. If you consider an ellipse at the ends of those cylinder, solid cylinder, then you can picturize that asymmetric like this. So this is an ellipse, and we have the cylindrical structure like this. So also we have that same. So I'm not considering spherical face here. Sorry, circular face. I'm considering elliptical face. So I will be having this as my, let's say this is my IA. This is my, I'm just representing. I'm not saying this is IA. I'm just representing that like this. And this is my C. So I'm not talking that this particular molecule will be having. I'm not talking about any molecule. I'm just representing that the analog. So this is the IA, IB, and IC. So since this is an ellipse, IA will not be equal to IB, and this too will not be equal to IC because this is cylindrical. As we can see from this figure, IC is not equal to IB, not equal to IB. Okay. Similarly, here we have this here. This one, this symmetric top also you can represent with this kind of a figure with the cylinder having circular face. Cylinder having circular face. So in this case, what is this? This is your IB and this is your IC. Your IB. This one is IA. But this IA should be smaller. So that cylinder, when you draw that, it should be smaller. So depending on that prolate and oblate structure, I'm saying. Let's say this is the base of your cylinder. So that this is your A, and that IA is smaller than IB. So similarly, you can use different picturization of the same. There are different kind of. Okay, so that's about the classification of these molecules. And now we will discuss a little bit about the rotational spectra. So this, I will just show how this exactly happening. This rotational spectra which is coming first. Then so if you consider any molecule, Or if you consider a dipole, we first consider a dipole. Let's consider a hydrogen fluoride molecule. And again, you consider H2 molecule, or you consider O2 molecule, or Cl2 molecule. So those molecules will not be having any dipole moment. For the case of HF, what is this HF? We have hydrogen molecule here, then we have fluorine molecule here. Here and here. This hydrogen will be having a positive charge, polarity of positive, and this fluorine will be having negative polarity. But when you consider those hydrogens do not have that opposite charge polarities. When you consider that hydrogen molecule or oxygen molecules, they will not have that opposite charge polarity. So these molecules uh, will not be having uh, any dipole moment. So they will not have any dipole moment. So these are having zero dipole moment because they are having same charges. So oxygen are having same atoms, same charges. But here we have positive charge, one positive charge corresponding to this hydrogen and negative charge corresponding to this fluorine, and they are separated with some distance. Then this will produce some dipole moment. This will be having some permanent dipole moment. All these are linear molecule. I'm saying all these are linear molecule. Not discussing about those other complicated molecules. This is saying about this linear molecule for understanding. These are linear molecules. We have permanent dipole moment for hydrogen fluoride. And for other molecules like H2O2 or Cl2 or any other molecule, they will not be having this uh, dipole moment if they are not having this equal and opposite charges separated by distance. And this configuration is called as dipole. Okay, so the molecule which are having permanent dipole moment shows microwave spectroscopy. The molecule with zero dipole moment is microwave inactive. Why is that? Because if you consider a plus charge here and a minus charge here, what will be the, suppose your uh, atom is like this, positive charge above and negative charge below. If it is rotating, then that positive charge will come here and negative charge will come here. Okay. Then again, if it is rotating, then your positive charge will come down. This positive will come here, and the negative will come here. It is rotating. This particular molecule, if you consider hydrogen fluoride, it is rotating. So initially hydrogen was here, then fluorine was here, then hydrogen will be here, and so it is rotating like this. So when they rotate, the charge will be like the charge position of those atoms will be changing, and this again will come plus here and minus here. And then again it will come to plus original position, then etc. So when it rotates, what is actually happening? If you consider that electric field, consider electric field of this particular scenario, we have electric field which is coming from positive to negative. So the positive to negative electric field would be there. So if I make it as a baseline, so I'll be having initially this electric field. then I will be having this scenario. Okay, so my electric field is now going this way, this point. I put it like dot here. Then we have up electric field. So I can represent it in the same fashion here. I can represent it like this. Then again it will become. Then again uh, down. I'm just representing its direction. So we have a continuously varying electric field here, like or continuously to. So if this molecule rotates, this dipole moment rotates like this, then that will produce some particular electromagnetic radiation, and this electromagnetic radiation is nothing but the microwave. Its frequency will come in microwave. So in order to possess this rotation, or in order to rotate these molecules, it must have this permanent dipole moment. Then only the molecule will rotate, and only those molecules with a permanent dipole moment will be microwave active. Only those molecules will be microwave active, and other molecules will be microwave inactive. If they are not having permanent dipole moment, then they are microwave inactive. So this is the basic process which is happening to these molecules, how these microwaves are coming. And also important thing is that if this molecule, for example, this hydrogen fluoride, which is rotating in a particular frequency, which is rotating in some particular frequency, let's say mu, and it will absorb same frequency. If some frequency is coming from the any external source and interact with this particular molecule, and if this incoming radiation is also having same new frequency, then only this molecule will absorb that frequency, and it will increase its frequency of rotation. Okay, so then for example, initially it is having new frequency, and one new frequency is coming from any external source interact with this molecule. Since both of them are having same frequency, it will absorb that frequency, and it will go to some, for example, two new frequency range. So the rotation frequency will be larger in this case. So the rotation will be very high. I mean, number of rotation per second will be larger. So two new will be the frequency. So if your energy level is here initially, after absorption of that energy, that particular frequency is coming from that external source, its energy level will be high. So if it was j equal to, for example, in this initial state, it was j equal to 0 state, then it will go to this j equal to 1 state. Is coming. Then it will absorb that particular frequency, and it will go to the higher state, higher energy state. Okay. Same fashion, it can reduce its frequency of rotation by emitting some frequency also. Okay. So when it comes back, it also emits frequency of. So that is basic action. So if you want to produce some microwave radiation from a molecule, we have to rotate that molecule. The molecule should have some rotation, and that can produce some microwave when that molecule uh, comes to some lower energy level. It will emit that microwave. Another way is that if you want to rotate a molecule, then you have to provide some microwave of frequency which has to match with the rotational frequency of the molecule. Then by that way, you can rotate the molecule with some more higher frequencies. Okay, and from that rotation or rotational spectra, as we discussed earlier, from that rotational spectra, if you study some rotation spectra of any molecule, then if you get that B value we discussed earlier, if this particular hydrogen fluoride, which is going to give you some frequency output. Okay, so that from that we can calculate what is B value, which means that if you are taking that output spectra, then you will be having different lines, okay, corresponding to this hydrogen fluoride spectra, rotational spectra, and take these two suppression of these two lines is emitted by this hydrogen fluoride spectra, and that will give you 2B, and from that you can calculate what is the value of B, and B will be given by H by 8 pi square IC, and from that you can calculate what is I, because all others are constants, and I is nothing but mu into R0 square. Mu you can calculate if it is hydrogen fluoride, mu will be the reduced mass of hydrogen and fluorine. Okay, you can calculate what is mu. From that, if you divide I by mu, I you will get from this spectra from here after calculating B. From that you will get R0 square. From this you can get R0, that is the intermolecular or interatomic distance of that hydrogen fluoride. So by using this spectroscopy analysis, you can calculate what is the suppression between this hydrogen and